We present a method for correcting human motion accelerations and velocities attenuated by low-pass filtering in motion capture. This is accomplished using a sparse set of high-rate inertial measurement units, or IMUs, on the body. Accurately capturing motion accelerations is important as they excite soft tissue dynamics. Using a spring damper mass system to represent soft tissue, we demonstrate conceptually the role of impact accelerations in exciting soft tissue motion. Two spring systems, one using filtered kinematics in blue and the other using true kinematics in red, are dropped onto the ground. Upon impact, we see that both systems have similar position traces, yet the system with filtered kinematics in blue has only half the impact acceleration. This in turn results in smaller mass oscillations that continue after the impact. To demonstrate our correction method, we equipped 5 subjects with a commercially available motion capture system. We chose the XSense Awinda IMU suit as it allows us to make motion capture out of the lab. This system contains 17 IMUs, which are placed on each segment of the body and sample at 60 Hz. We also instrument subjects with 10 X-Patch high-rate IMUs, which sample at 400 Hz. These sensors are sparsely placed on the feet and the torso. Once instrumented, we had subjects perform a number of dynamic activities. The first was a series of basketball jumps. Data were recorded in real time by the XSense motion capture system and post-processed in MVN Studio using the multi-level HD post-processing pipeline. Visually, this system indeed captures subject jumping motions. Captured motion was exported to Maya and used to drive a human skeletal rig. We attached locators to the rig at the location of high-rate IMUs, which we used to predict high-rate IMU accelerations with forward kinematics. Vertical linear accelerations exceeding 25 meters per second squared from the high-rate IMU at the pelvis were used to identify impacts. Once impacts were found, we superposed a correction function to the rig generalized coordinates to match high-rate IMU accelerations. In the corrected motions, we observed little adjustment to generalized coordinates such as vertical position, but this still yielded substantial increases in impact accelerations. Small changes in ankle angle also yielded larger changes in ankle dorsiflexion velocity for jumping impacts. For one subject, we made additional motion capture measurements with a 10-camera Vicon optical marker tracker. Vicon data were captured at 240 Hz and post-processed using Vicon Blade and exported to Maya. The subject only performed basketball jumps due to the limited capture area of the Vicon system. XSense and Vicon data differed on average by less than 2 cm in pelvis vertical position and 3 degrees in ankle angles. Thus, similar corrections to impact accelerations and ankle dorsiflexion velocity were made to both systems. The effect of the increased impact accelerations is evident in the excited soft tissue dynamics. We used original and corrected motion capture profiles to drive a previously developed male soft tissue rig, shown here with an enlarged stomach. Corrected motions produced a 143% increase in relative soft tissue motion, with particularly large differences near the stomach. Side by side, we can more clearly observe differences in soft tissue motion and the small vertical position correction around the impact. A similar increase in soft tissue motion is seen in high-speed video of one subject jumping on a cushion, which mimics low-pass filter attenuation, and jumping on hard ground. Our second dynamic activity was a run outdoors. To get outdoors, we had subjects descend several flights of stairs. Interestingly, stair descent did not produce accelerations that exceeded our detection threshold. The running activity was processed in the same manner as the basketball jumping activity. We again observed small corrections to vertical positions and large increases in vertical acceleration, as well as small corrections to ankle angles and large increases in ankle plantar flexion velocity. Due to the milder impacts in running compared with basketball jumping, we observed smaller excitation of soft tissue during this activity. Acceleration corrections yielded small increases of 10% in relative soft tissue motion during running sequences. Here, we demonstrate a specific implementation of our correction method using the XSense Awinda IMU motion capture suit in basketball jumping and running. However, this method can be generalized to work with other motion capture systems, such as the Vicon optical tracking system, to correct impact accelerations in other dynamic activities. As observed in our animated examples, corrected accelerations can be paired with soft tissue rigs to generate realistic character animations.